This is our first problem under the special polytropic process. Please take your time to read and understand the problem. Hydrogen is a working fluid in this problem. We are also given its initial pressure, temperature, and volume prior to the expansion process. At the end of the expansion process, the final pressure is equal to 14.7 psi. We are also given the polytropic exponent n for the process, which is equal to 1.3. The specific heat ratio of hydrogen is also given. As a final note, we can say that hydrogen is undergoing a special polytropic expansion process. From this given information, we shall compute for the non-flow work and the amount of heat transferred in kilojoules. In addition, we shall also compute for the change in entropy in kilojoules per Kelvin. Now let's sketch the PV and TS diagrams for this process. Since we have an expansion process, we can already be sure that the sketch of the PV curve will start from the upper left at point 1 and end at the bottom right at point 2. This will also be the shape and direction of the curve at the TS diagram. Now before we proceed, I would like to explain what the last sentence in the problem means. When we say that we should assume constant specific heats in our solution, it is another way of saying that we are going to use approximate solution in solving the problem. Now let's start with solving the non-flow work. This is the formula for finding the non-flow work during a special polytropic process. Notice that only the final volume V2 is the unknown quantity in the right side of this formula. But we can compute for it using the equation for the PVT relationship for a special polytropic process. By isolating V2 on the left side of the equation and substituting all the known values in the right side of the equation, we will now be able to compute for the value of V2. Now substituting all the known values in our formula for the non-flow work, we will now be able to compute for the value of W sub n, which is equal to 288.5 BTU. The next quantity that we are going to solve is the amount of heat transfer. Remember that the approximate solution for Q corresponds to this formula. Now if you will look closely in this formula, the values of the four quantities in the right side of the equation are unknown to us. We do not know M, Cn, T2, and T1. So we shall find a way to express them in terms of our given quantities, which in this case are the pressure, volume, and volume of hydrogen at the initial and final states. First, let us write the specific heat for polytropic process C sub n in this way. Then we replace C sub V by its formula R over K minus 1. By rearranging the quantities at the right side of the equation, we will be able to see more clearly the product of the mass, specific gas constant of hydrogen, and the change in volume or a change in temperature of the gas. We know that we can replace this part of the formula by P2V2 minus P1V1 based on the equation of state of ideal gas. Now, if you will look at the formula that we have just derived, the values of all quantities at the right side of the equation are already known to us. So by substituting all the known values in the right side of the equation, we will now be able to find the value of Q to be equal to 72.1 BTU. The last quantity that we're going to compute is the change in entropy. The approximate change in entropy can be found using this formula, but since we do not know the values of the initial and final temperatures, We replace the ratio T2 over T1 inside the logarithm by P2 over P1 raised to n minus 1 over n instead. In this formula, there are two quantities which we do not know the values of: the mass of hydrogen and the specific heat C sub n. C sub n can be computed using this formula. Since we do not know the value of the specific heat at constant volume of hydrogen, we replace it by the ratio of the specific gas constant of hydrogen over K minus 1. Finally, we also replace the specific gas constant of hydrogen by the ratio of the universal gas constant and the molecular weight of hydrogen. By substituting all the known values in this formula, we will finally be able to find the value of C sub n, which is equal to negative 643.75 foot-pound force per pound mass Rankine. Before we proceed, notice that unlike the specific heats at constant volume and at constant pressure, the specific heat for special polytropic processes can have a negative value. Next, we compute for the mass of hydrogen. We can compute for this using the equation of state of ideal gas. By using the given initial pressure, volume, and temperature in our formula, we will get 290-pound mass as the mass of the hydrogen gas. Finally, by substituting all the given and computed values in our formula for delta S and converting foot-pound force to BTU, we will get 118.5 BTU per Rankine as the value of the change in entropy.